Hello and welcome to another presentation, this time on arithmetic sequences and series and sigma notation. So let's have a little look at sigma notation then. Right, well, I'm sure you've picked up this from some of the PowerPoints, and we're just going to go through the general ideas of what sigma notation really means for the symbols and numbers inside. Let's take this example straight away. If we write sigma r squared, or the sum of r squared as I prefer to pronounce it to the students, from r equals 1 to r equals 7 of r squared, all that simply means is you're going to start by plugging in 1 and you're going to square it, because that's what the function's telling you to do. Plus, because sigma means sum, it means add. Now plug in 2, square it, plus. Now plug in 3, square it, plus, all the way up to 7 squared. And then you've got your final answer, essentially. You've got the answer which I believe, let me know if this is incorrect, but I think 1 squared plus 2 squared all the way up to 7 squared will be 140. So that's the way the actual notation works. It's about plugging the values in from the bottom of the summation and the top of the summation, plugging them in gradually and systematically and summing it, so it creates a series. Okay, let's have a look at this one. This is really just to show you that summations don't have to start from 1, they can start from 3. Notice I haven't written down r equals 3 and r equals 7 here. You don't have to do that. You can do that, but you don't have to do that, because it's pretty obvious that r is a variable in this particular summation. So this time we're not doing r squared, we're going to do 2 to the power of r from 3 to 7. Well, we start by plugging in r is 3 and we get 2 cubed, plus, then we plug in r is 4 and you get 2 to the power of 4, plus, so on and so forth, all the way up to 2 to the power of 7. Now I believe that equals 248. So these actually take values. Now the last one I'm going to show you doesn't actually take a value, because I'm not going to define what a subscript I stands for. Now, in some of the questions in the unit assignment, we actually have a formal definition for a subscript I, and it's going to be a bit clearer what exactly this means, but you don't actually need it. If I'm written down just that, and you'll notice this time it's clear I is my variable. They've just changed the letter, because we have I equals 1 written down at the bottom of the summation, and then we're dealing with a subscript I, and the whole of this summation apparently equals 6. Well, if you want to write this without sigma notation, you could just write this as, well, plugging at I as 1, then plug in I as 2, then plug in I as 3, then I as 4, add all those terms together. What we're really saying here is A1 plus A2 plus A3 plus A4 equals 6. Now when you use that subscript notation as well, we normally use that in terms of sequences, so it's pretty clear these are the first 4 terms in a sequence. Okay, let's talk a little bit now about arithmetic sequences. Now, the only thing which defines an arithmetic sequence, and I'm sure once again you've picked this up from the PowerPoints, but it's any sequence of numbers where the difference remains constant between the terms. These are also called linear sequences. In fact, I almost prefer to call them linear sequences, because that's what I call them. That's how I describe them to my classes at GCSE. I say, oh, it's a linear sequence if it's a constant difference. If the second difference is constant, then it's a quadratic sequence, so on and so forth. So for me, I actually quite like the term linear sequences, but if you see arithmetic sequences, it means exactly the same thing as a linear sequence. So let's have a look at some examples. Here we've got 1, 4, 7, 10, 13, and let's just write down straight away. Let's write down the nth term for this sequence. Nth term well, I hope you're not too bewildered if I just write this down straight away as 3n minus 2, simply because it's the 3 times table moved back 2. I just want to make a point though. In A level, we don't normally use the phrase nth term. We actually use just a subscript n, and this ties in with my example which I just gave you. That implies nth term. Sorry, I've written the n a little bit large there, but in A level we probably just write it down like that, an equals 3n minus 2. That's nice and clear and simple. It'll be the same for the next one, if I'm going to call it a, the sequence an again. This time though it's going down, and we're going to need to start, it's going down by 1 each time, and we're going to need to start at minus 0.5. So it's going to be minus 0.5 minus n. And similarly for the next one, but this one's actually increasing, we'd probably write down an equals 0.05 plus 0.05n. And that is the nth term for those three sequences. But like I say, in A level we tend to denote it AN. Okay, a point which I want to make straight away is that in A level studies we're not just interested in the nth term, we're often interested in summing the sequence as well. This is going to come up in a couple of slides time. In fact, I'm going to prove to you the result for the sum of an arithmetic sequence. But yeah, just to point out, it's not just the nth term we're interested in. Okay, let's just get rid of that notation. Okay, generalizing an arithmetic sequence. All arithmetic sequences are of this form: A plus D, A plus 2D, A plus 3D. This is of course where A stands for the first term and D stands for the common difference. And you can certainly see this if I just take the fairly simple arithmetic sequence I was using initially, 1, 4, 7, 10, 13. You can see the first term A is 1, the common difference is 3, so the next term will be 1 plus 3, the term after that will be 1 plus 2 times 3, the term after that will be 1 plus 3 times 3. That's why that is the general form of an arithmetic sequence. This nth term here, this is actually what you might call the nth term of the sequence. It is the nth term generalized. And often when I teach this to students in A-level, or sometimes anyway, a student's quick to say, why didn't you tell me this formula when I was doing linear sequences in GCSE? And I always give them the same answer, which is, well, I prefer you to understand it as a translation of just a shift of basically a times table moved forward or moved back. You see, the more people depend on formulas, the less they sometimes understand of what they're actually working with. But in A-level, we like to formalise results, and formulas obviously do exactly that. We like to generalise results, and so, yeah, I then show them this lovely little formula. Nth term equals A plus n minus 1d, but once again, I'm going to write it down underneath as an equals A plus n minus 1d. And I think that's how the formula appears in the Edexcel formula book at A-level. So, yeah, in fact, the last term is a general rule for finding the nth term of any linear sequence, and you can use it. Let's just quickly show how it would have worked for the 1, 4, 7, 10 one. We would have had an equals A, which is 1, plus m minus 1 times d, which is 3. And if I now simplify and multiply out the brackets and then collect the terms together, I get 3n minus 3 add 1, which is going to be minus 2. So I do get exactly the same sequence which I said before, exactly the same nth term formula which I suggested I would have as before. So there we go, a little formula essentially for always finding the nth term for any linear sequence. Pretty handy, especially for some of the questions we'll be looking at later on. Okay, so let's actually take off some of these. Yeah, we're going to be summing an arithmetic sequence here. Sorry, I've actually gone too far through the slide. Let me just talk you through it bit by bit. You'll see as well I've got a little picture of Gauss here. Carl Gauss was a famous mathematician. In fact, you could even argue that he possibly is the greatest mathematician of all time. He's certainly right up there with Newton, right up there with a host of other fantastic, stellar mathematicians, along with all kinds of mathematicians, really. He is, he discovered so many things. But there's a famous story that his teacher, when he was about 8 years old, when he was back in primary school at least anyway, his teacher asked him to add up the numbers from 1 to 100. Not just him, but the whole class. Really just to keep them busy for, sort of 20 minutes whilst the teacher could, I don't know, put his feet up and read the paper. I'm not too sure. But quick as a flash, Gauss just wrote down the answer, 5050, which is the answer to 1 plus 2 plus 3 all the way up to 100. And the teacher obviously was rather impressed. But all he'd done, and this comes up actually in another one of my presentations, all he'd actually done was paired up the terms, really just like I'm about to do here. So let me just talk you through my reasoning. We could call a sum from 1 to plus 2 plus 3 all the way up to 100, S. And then we could write it down backwards underneath. Now I want you to remember the technique I'm using here, because it is in fact really useful for the general proof of an arithmetic sequence. I always show students this first because I think they understand the general proof of an arithmetic sequence better. Now this will work for any arithmetic sequence. This is an arithmetic sequence because the difference is constant, it's always 1. If we write down the sequence backwards underneath, you will see that we've got 100, 99, 98 all the way down. And now if we add both this and this together, we're going to add both of these equations and we're going to get s plus s on the left hand side, which is 2s. But look at every term here. 1 plus 100 is 101. 2 plus 99, well that's 101 as well. 3 plus 98, well that's 101 as well. All the way up to the end, to where you get 100 plus 1, well that's 101 as well. You're always going to get exactly the same number. And what's more, how many numbers are there? How many 101s do we have here? Well, we have 100 101s because there were 100 terms in the sequence up here. And therefore, all we really need to do is 100 times 101, and that's going to give us the answer of 5050. That's what Carl Gauss did when he was 8 years old, which I think is really quite impressive. If anybody ever does that in my class, I like to show them actually. I always give students a chance to say, can anybody spot a quick way of doing it? Sometimes you give them a little bit of a hint, and students do understand this. They do get it. They do get there in the end. Give them a few minutes, so obviously it takes some serious thinking time. Okay, so that is a classic sum of an arithmetic sequence. Let's try and generalise that result using our a plus d, a plus 2d, all the way up to a plus n minus 1d. And I hope you remember that this last term, that is the nth term. So this is for the sum of n terms. That is the nth term there. Well, we're going to use exactly the same trick. We're going to write the formula down backwards. So we've got a plus n minus 1d first, then a plus n minus 2d, all the way up to a plus 2d, a plus d, and just a on its own. And now, what we're going to do is we're going to add those two together. We're simply adding the left-hand side and the right-hand side. Now, when you add Sn plus Sn, you're going to get 2Sn. But now, if we just add this one to this one, if you add a plus n minus 1d, do you agree that goes to 2a plus n minus 1d? Hopefully you can see that's true. Now if we add this one to that one, if you add a plus a, you're going to get the 2a. And then if you add d to n minus 2d's, well, if you have n minus 2d's and you add a d to it, sure enough you get n minus 1d's. We should be getting exactly the same term each time, because just like with the 1 plus 100, 2 plus 99, 3 plus 98, you always get exactly the same term if you do this to any linear sequence. Write down any linear sequence forwards, then write it down backwards, and you'll notice that each term sums to the same term. It really, really works. And it happens right at the end as well. If you add this one to this one, you get 2a plus n minus 1d. If you add that one to that one, you get 2a plus n minus 1d, so on and so forth. Now really, the only other thing we've got to worry about is how many of those terms are there? Well, once again, there are n terms, because remember, that last term was the nth term, and therefore we have n terms there. Now, we can actually come up with a final formula. Well, we can say there's n lots of 2a plus n minus 1d, so we'll write that as n open bracket 2a plus n minus 1d, and then the way the formula is normally expressed is Sn equals n over 2 multiplied by 2a plus n minus 1 lots of d. And it's done. That is the general rule for the sum of an arithmetic sequence. So that's a proof they occasionally get asked in A-level, at least certainly on the Edexcel syllabus, they do occasionally get asked that proof. And that really gives me, well, I've gone over two of the formulas which I'm about to present to you. These are useful formulae. I've also included a third one actually as well, which I'm going to show you in a second. So for any given arithmetic sequence, and it only works for linear sequences, if we define it in this form, and this is just another way of notating it, a1, a2, a3 all the way up to an, that just means first term, second term, third term, all the way up to the nth term. We've got an equals a plus n minus 1d. That's just the nth term formal definition with the lovely little trick for always correctly finding the nth term for any linear sequence. We've got this result for finding the sum of any linear sequence. And then I also want to mention this one. This is what I describe as the inductive definition of a linear sequence. It's also called the iterative definition. You could also call it a recurrence relation. It is simply a way of describing in any linear sequence how you get to the next term from the last term. And because in any linear sequence we just add on the common difference, all we've got is next term equals last term plus common difference. That's going to come in handy on one of the questions we do towards the end of the PowerPoints. Okay, sorry about that A-3 starting down there, ignore that for a second. Let's take a question. The fifth term of an arithmetic sequence is 17 and the 13th term is 57. Find the first term and the common difference. Now it is possible, and often my students point this out, they often believe, rightly as well, that they can just do this by essentially finding the gap between the 5th and the 13th term, so doing 57 minus 17 is 40, and then figuring out when it's 8 terms later, so I need to do 40 divided by 8, that's going to be 5, that gives me the common difference, and then I can reverse engineer that to find the first term. They are of course correct, but I like to formalise it for them by using my standard results. So the fifth term, well, if you remember, an equals a plus m minus 1d, yeah? So a5 is a plus 4d. A7, if you're working out the 10th term, it would be a10, well that's a plus 9d. It's always one less than the term number. So the fifth term, which would be a plus 4d, that's 17. The 13th term, which would be a plus 12d, that's 57. Now we're going to do essentially exactly what the students might describe. We're going to subtract them because we've got simultaneous equations there. That gives me 8d is 40. Sure enough then d is 5, and using d equals 5 I can plug it into either the first equation or the second equation, and I'll get a is minus 3. And that's all there is to it. Hope that makes sense. Let's try another example. That's a fairly straightforward one. Let's try a trickier one. Okay. A sequence is defined as a3 is 3, and then this time I'm going to define it inductively. I'm going to say an plus 1 equals 3an plus k. Now I will straight away point out this is not a linear sequence, it's not an arithmetic sequence, but it might come up in the unit assignments. In fact, I think a question similar to this does come up. Okay, given that we're trying to find, given that we know that the sum from I equals 1 up to 3 of AI is 34, we're going to try and find the value of k. Well, it's all about understanding what the notation means. Mathematics, it really is. And all this is saying, as I mentioned earlier, all this really means, we really need to find A1, A2 and A3 because we know A1 plus A2 plus A3 equals 34. Now to find A2 from A1, you can just do A2 equals 3 times whatever A1 was, and I'm using this inductive formula here. If we just plug in A1 as our AN, we can then work out A2. So we just do A2 is 3 times 3 plus k, so that's 9 plus k. Likewise for A3, but this time we'll be plugging in the last result. So A3 is 3 times 9 plus k, which is 27 plus 4k. Now we can find the value of k, because we know that the sum of the first 3 terms, well that's just going to be the first term plus the second term plus the third term. That equals 39 plus 5k, but this also equals 34, so 34 equals 39 plus 5k. All I've done here, if you're just worried about the missing step here, all I'm saying is, sorry about that, my mouse pointer keeps misfiring. Yeah, so all the missing step, all it is just 39 plus 5k equals 34, and I've solved that, and I've found the value of k to be minus 1. So look out for those little inductive sequences, they can sometimes confuse people. Let's have a look at another question though. This one's a good question. It simply reads, find the sum of all multiples of 6 from 1 to 500. Now, if we're going to do this, we really need to find out how many multiples of 6 there are before 500. So it's going to go 6, 12, 18, plus, blah, 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 all the way up to the last term. Now, as I've written here, to find how many terms there are, simply do 500 divided by 6. and then you'll see that's 83 and a third. So we need 83 terms, because all we really need to do, I mean, you can find out which term that is as well. We don't really need to know this, but if you do 83 times 6, you can find out the 83rd term as well. All we need to do then, we've got our first term, a is 6, we've got our common difference, d is 6, we've got our number of terms, 83 terms. We can just plug it into the sum formula, and if you plug in those values into that equation, you will find the answer is 20,916. Now, there are more tricky questions than this, which pop up in the next part of the module. There are online examples which take you through the trickier questions as well. It will be, you'll just see my hand actually writing down the solutions. But yeah, have a look at the tougher examples as well and see how you find them. Always have a go at them first, and if you get stuck, you can look at my online example solution. Okay, that concludes this little presentation. I hope you found it useful. Best of luck with the rest of the course.